Okay, and here we are. This is our final installment. We're going to find the rotational inertia by integration, and this time we're going to look at objects with cylindrical symmetry. Okay, so one more big example of how to use the inertia integral. Alright, let's take a few minutes and just have a look at this picture. This shape is a hollow cylinder, and its axis of symmetry is running right up through the middle. What we're going to be looking at is a very thin shell within this hollow cylinder, and the thin shell is given in the picture there. It's like a sleeve that slides down into this cylinder, and this is a little bit different than the last case. If you can think of it, it's like a piece of paper rolled up into a tube. The thickness of the piece of paper is dr. The radius of that piece of paper is going to be r. And so when we do our integration in this problem, we're going to be integrating over that paper-thin sleeve that has cylindrical symmetry and that fits within the cylindrical shell that we have in the picture here. So let's see how that's going to work. Okay, for our starting point, we are going to recognize that the mass in this case is equal to density times volume. And what we're going to do is we're going to change that into kind of its differential form. So dm is going to be equal to rho dv. So the symbol for density is a rho. It's the Greek letter r, the lowercase r. And if you're looking at a very small chunk of this material, you could say that its mass would be equal to its density times a very small chunk of its volume. Okay. Now, the tricky part here and the different part is that when we talk about the differential mass element, dm, what are we talking about? What does that look like? When we talked about a rod, it happened to be a small segment along the length of the rod. But if you have something with cylindrical symmetry, then when we talk about the thing that we're using to integrate, we're going to talk about this thin sleeve. Okay? Now, this is the hard part. So you have to look back up at the picture. And when we talk about dm, dm is the mass of that sleeve. Okay, now remember, the sleeve has a radius of r and it has a thickness of dr. Okay, so if you wanted to find its mass, what you would be doing would be taking the circumference of the sleeve, which is going to be equal to 2 pi r, and you're going to multiply then by the length of the sleeve L, and then you're going to multiply by the thickness dr. Okay, so what you're getting is that stuff in the brackets is really the volume of the sleeve. Okay, it's kind of a different way for us to look at a differential element. So 2 pi r is circumference, L is the length of the sleeve, and dr is the thickness of the sleeve. And when you multiply those three things together, you get a volume. You can tell by the dimensions, r times L times dr will give you length cubed. So it matches up with what we expect for a volume element. And then you multiply it by density, and that's going to tell you the mass. So I'm going to repeat this again. dm is the mass of that sleeve that we are sliding into our cylinder. That very thin sleeve that has a radius of r and a thickness of dr. Okay. So now let's go and see what we can do with that. We are going to have a look at the inertia integral. Okay, that's how it's defined. It's r squared dm. And of course the game that we play again is we want to get rid of dm, and we would like to replace it with something that's easier to integrate. Typically a geometric parameter such as dr. So I replaced dm with the expression that I just went through all that work to get. Okay, so that gets plugged in. And I'm going to integrate this expression now in terms of radius. And my endpoints of integration are going to be R1 and R2. Now let's go back up for a second and look at the picture. You can see that R1 and R2 are going to be kind of like an inside and an outside endpoint. Those are limits. So when I actually solve this integral, I'm going to have the freedom to make the actual cylinder as thick or as thin as I would like. If I would like to do a cylinder which is solid, I would make R1 equal to 0. If I would like to do a cylinder which is completely hollow and has all of its mass at the edge, then I would make R1 equal to R2. So those would be two limiting extreme cases. Okay, so we're going to have a lot of freedom here to choose R1 and R2, and that's what we want. Okay, so let's continue. And we're going to factor out a bunch of constant things here. 2 pi rho L. We're left with r cubed dr. And again, we're integrating from R1 to R2. Okay, this is actually not too bad. When we integrate r cubed, it becomes r to the 4th. We bring out a factor of 1/4. Ooh, this looks fun. Okay, what you have here would be the expression for the integral when you've substituted your endpoints R2 and R1. Coming over to the right hand side, I'm able to factor that out. Okay, that's kind of a special case. B to the 4th minus a to the 4th factors out here kind of nicely. And at this point, you might stop and say, well, that's about as far as we can go. We have an expression here. The expression has R1 and R2. We can tune those and put in it whatever we want. The expression also has a length in it, as in the length of the cylinder. But the one thing the expression does not have is it does not have the mass of the cylinder. We would really like to put that into the final expression. Now, in truth, the mass is showing up in the density here, in this term rho. But it's not really obvious there. So what we'd like to do is we would like to do one more substitution. And we would like to get rid of the rho, and we would like to bring mass back into this formula. Now, there's a little bit of a trick here. Just a little. And hopefully by now you're following along. And the trick is that the mass of the thicker shell, that is, let me say it this way, the mass m of our hollow cylindrical shell, okay, so not the paper thin one, but the entire hollow cylinder that we're integrating, is going to be given by this expression. It's going to be rho times pi times L times R2 squared minus R1 squared. Okay, what does that mean? Where does that come from? Well, forget about the rho for a second. Let's cover that up. What you have over here is basically area times height. And you're subtracting the area of the inner circle from the outer circle, and you're multiplying by the height of the cylinder. And what that's going to give you is the volume of that hollow cylindrical shell. So when you take the volume of the hollow cylindrical shell and you multiply by rho, the density, you're going to get the mass of hollow cylindrical shell. So let's come back up and look at that for a second. We are now talking about the entire hollow cylindrical shell. In other words, the one that extends from R1 all the way out to R2. Okay, so we're no longer talking about dm, which is the small paper thin shell, but we're talking about capital M, which is the big overall hollow cylindrical shell that we want. Okay, and so that's what we have there. So if you have a look at that expression, you can see there's an r2 squared minus r1 squared. That shows up here, as does L and pi and rho. And so we're going to substitute out a few things here and replace them with m. This actually is kind of nice. Okay, that's going to simplify things quite a bit. And our final result is going to be 1/2 m times r2 squared plus r1 squared. You see what happened? We got rid of the difference term by our substitution. We also got rid of rho and pi and L, and we now have something different. Now, interestingly, L doesn't factor into this at all. The length of the cylindrical shell does not matter. The only thing that matters are the distances that are measured sideways from the axis of symmetry. One last thing I'll finish up with, and that is look at your extreme cases. For example, if you set R1 equal to 0, that's the case where you're looking at a full cylinder. Okay, it's not hollow at all, it's full. And the expression that you would get would become 1/2 mr squared, where r is the radius of the cylinder. Okay, hopefully you can see that by inspecting the formula we have in the box. That actually matches up with the formula that we saw in table 9.2. That was one of the formulas on the list. There's one other extreme we could take. What happens when we make this cylindrical shell very, very thin? And you can do that by setting R1 equal to R2, and that places all of the mass at the outermost edge of the shell. And when you do that and set those two things equal, you end up canceling out the 1/2, and you're left with mr squared. And hopefully you recognize that too, because that was a result that we pointed out back when we looked at the table of simple shapes. A hollow cylindrical shell has a rotational inertia of mr squared. So one more time, we've applied the definition for the rotational inertia in integral form, and we've come up with a nice general result that can be used for a variety of cylindrical symmetries. And we did have to play a little bit of a trick here, and I think the hardest part of this whole problem is recognizing that the differential volume that you're dealing with is that paper-thin cylindrical shell that has a thickness of dr. That's the difference here, and this is the first time that we've seen this. And we will be looking at this type of integral again as we go on in this year. Okay, then see you later.